Welcome to the Obliquencer Video Manual, Part 1. In this video, we will cover the submodules which comprise the Obliquencer Sequencing System, and their basic functions. Chapter 1, Inputs and Outputs. At the top of the Obliquencer is a row of jacks, which allow the user to input and output signals to and from the Obliquencer. There are 6 outputs and 2 inputs. The groups of 2 jacks found at the left, center, and right are 3 sets of gate and controlled voltage outputs. The gate outputs are indicated by a simple square wave icon, and the controlled voltage outputs are indicated by representation of various stepped voltage levels. The 2 remaining jacks with arrows pointing inward are the external inputs, which accept on/off gate, trigger, or clock inputs. In this example, the gate and controlled voltage outputs have been patched in groups into the gate and volt per octave inputs on 3 external analog synthesizer voices. Chapter 2, Gate Output Matrices. Below the controlled voltage and gate outputs are 3 separate patching matrices. These matrices allow the user to patch the various internal clock and gate pattern generating submodules into the gate outputs. In this example, the gate outputs have been patched into the gate inputs on external envelope generators, which are in turn patched into voltage controlled amplifiers to shape the volume envelope of 3 separate simple synthesizer voices. One of the internal clock modules has been patched into all 3 of the gate outputs, allowing us to hear the 3 external synthesizer voices the Obliquencer is patched into, triggered in synchronization. Chapter 3, Controlled Voltage Tuners. Below the gate output matrices, you will find 3 rows of trim pot tuners with illuminated triangular icons above them. These tuners can be accessed in any order depending on the configurations of the melody and harmony generating sequencers. The tuners set the voltage levels for the corresponding controlled voltage output jack above each group. The intended function of the tuners is to be set in advance, so that corresponding positions of each controlled voltage output produce corresponding controlled voltage levels, allowing for generation of spontaneous harmonic accompaniment on the 3 controlled voltage channels. The central group of tuners directly correspond to the activity of the melody ripple sequencer and melody sequencer inversion matrix, which will be covered in detail later in the video. The left and right set of controlled voltage tuners correspond to the harmony registers, which select their tuners by continually reading the state of the central melody ripple sequencer, and switching to the presently active tuner number upon a gate command. This can be thought of as a sort of digital sample and hold, which samples a tuner number on a low to high clock transition, and holds that tuner until it sees a new low to high clock transition, at which point it switches to whatever tuner is active on the melody ripple sequencer. The input clock for the harmony registers is set by the patch matrix directly below the tuners. Chapter 4, Clocks. The clock modules are simple square wave low frequency oscillators. These modules are typically used for clocking other modules, and can be found on the patch matrix for every other submodule. The large knobs on the left and right are rate controls. The indicator light below the knob illuminates the clock icon each time the clock goes high. Chapter 5, Decade Rings. The decade rings are found in the circular rings surrounding the clock modules. Despite their proximity to the clock modules, they are independent modules and are not directly related. The decade rings are gate sequencers which produce 2 to 10 step gate patterns. The clock matrix below the rings patches the clock input to the sequencers. Each time a low to high transition is detected at the clock input, the sequencer advances by 1 step. The outer ring of patch points selects which steps in the sequence will output a gate signal. The inner ring sets the overall number of steps in the sequence, resetting at the earliest patched step. If no pins are patched into the reset ring, the sequence defaults to 10 steps. The square patch point in the bump at the top of the decade ring inverts the pattern, making all on states off and vice versa. The icon for the decade ring illuminates whenever the module is outputting a high state. In this example, the clock input has been patched from one of the clock modules, and the output of the decade ring is patched to one of the harmony registers, and one of the gate outputs, triggering the selection of a new note, and the amplitude envelope of an external synthesizer voice. Chapter 6, Ripple Gate Sequencers. In the central section of the Obliquencer, there are 5 columns. The 2 outer columns, on the left and right sides, are the ripple gate sequencers. The ripple gate sequencers divide an incoming clock into progressively longer divisions, with the top round patch point dividing by 2, the next point down dividing by 4, the next dividing by 8, 16, 32, and so on, doubling in each position, up to a division by 4096. Depending on the incoming clock rate, it can take a very long time to witness transitions from the bottom divisions. The clock is set by the clock matrix at the bottom of the module section. The 2 ripple gate sequencers and the ripple melody sequencer, covered later, all use a common clock. The 2 patch points to the left and the 2 to the right of the clock matrix trigger a reset of the sequence, from either of the external inputs, or from the reset points of the decade rings. The icon at the top of the column illuminates on each positive gate output state. The square-plated patch point directly below the illuminated icon inverts the pattern, making each high state low, and vice versa. In this example, the output of the ripple gate sequencer is patched into one of the gate outputs, triggering the amplitude envelope of an external synthesizer voice. Chapter 7, Ripple Melody Sequencer. The central 3 columns on the Obliquencer comprise the ripple melody sequencer. In combination with the melody inversion matrix, described in the next chapter, the ripple melody sequencer forms the melodic heart of the Obliquencer. The function of the patch positions is identical to those of the ripple gate sequencer in that they represent divisions which double at each patch point as you descend the column, but in this case, they do not provide a gate output, but rather trigger controlled voltage tuner selections. As mentioned earlier, the activity of this sequencer is directly represented in the central set of controlled voltage tuners, and is also used as an input to the harmony registers found on either side. The ripple melody sequencer is a 3-bit binary system. Each column represents a bit, with the 3 bits adding in different combinations to create 8 different potential output states. Note that at the top of each column, there is a triangle icon with a dot in one of its corners. Next, note the triangle indicators above each tuner. In the tuner icons, you will see the combinations of bits that activate each tuner. The tuners are counted from 0 to 7, which is 8 positions. With nothing active in any of the columns, the output rests at the first tuner, or the 0 position. With activity in the first column, the number 1 is added. With activity in the middle column, the number 2 is added. And with activity in the right column, the number 4 is added. By adding 1, 2, and 4, you get the number 7. In this example, the patches are set up so that the number 1 is added every other clock transition. The number 2 is added and held every 4 clock transitions, and the number 4 is added and held high every 8 clock transitions. The end result of such a setup is an ascending pattern, counting through the 8 tuners in numerical succession, as the combinations of bits add from 0 to 7. Chapter 8, Melody Inversion Matrix. The melody inversion matrix is found in the 3 rows of patch points above the ripple melody sequencer. Note the vertical line connecting each row to one of the melody bit indicators below. It is called an inversion matrix. because a high input signal patched into one of the bits will cause that bit to do the opposite of whatever it is otherwise doing. In its most basic use, with nothing patched in the ripple melody sequencer, the melody inversion matrix simply allows for the activation of each of the 3 melody bits from the other modules within the Obliquencer, because it inverts from off to on. In this way, the user can create patterns through other methods than the ripple sequencing method. When used in combination with the ripple melody sequencer, the inversion matrix alters the patterns generated by the ripple melody sequencer. In this example, we see the ripple gate sequencer outputting a high state at a division twice as long as the longest division used in the ripple melody sequencer. This high state is patched to invert all 3 melody bits, so that their off states become on, and vice versa. The end result of this action is a reversal of the pattern from ascending to descending. This is a very basic demonstration for the purpose of clarity. Thank you for watching the Obliquencer video manual, Part 1. In Part 2, coming soon, we will cover how to tune the Obliquencer controlled voltage tuners.